Hey guys, I decided to make some videos about deep convolutional neural networks. Actually, my technical fields can be described in three main topics: wireless communication, digital signal processing, and deep learning with an image processing approach. The incoming videos will contain some topics about the applications of DCNN in image processing. These topics will take about 8 videos, which I hope I can complete and make a playlist over them. The difficulty of topics will increase gradually. The pre-requirements of utilizing these videos are quite minimal. Maybe a general idea of what neural networks are will help you understand the topics better. But you should consider what concepts matters for you and whether ARC's DCNNs related to it or not. The materials of these lectures are divided into 8 topics till now. First, I explain the general idea of a simple convolutional layer and present an intuitive approach to how these layers work. In the next part, I go into the mathematics of neural networks. In the third topic, I introduce some of the most famous convolutional layers. Fourth topic includes the techniques that are used commonly in designing modern convolutional networks. The fifth topic will contain data augmentation, which is a very important topic in image processing. Transfer learning is a popular method for using pre-trained models to solve image processing tasks with deep learning. The last two topics will include advanced topics about convolutional networks, and each one includes some papers that have been recently published in this field. We won't go into any implementation using platforms like TensorFlow or PyTorch. We study these topics theoretically. Maybe I'll consider some videos about implementation and code-based approaches. Now I start with the first topic. How does a convolutional layer work? To solve complicated tasks, we can break these tasks into some subsections. Each section will solve a part of this big problem, or complicated task, or any mind-blowing topic. We imitate the same thing in image processing. We break each image into different subsections. We extract different features from each image, which helps us to solve our image processing task. For example, we have lots of photos of dogs and cats, and the task is to build a deep learning based model to classify cats and dogs. In other words, we want to label which image is a cat and which one is a dog. We assume each photo just contains one of these two animals, and each photo contains only one animal. Maybe you find these assumptions too rigid, but for now we should consider them, and in the next sections we'll figure out how to deal with these two assumptions. Back into the main topic. To distinguish the animal, we can focus on the different parts of these animals. For human beings, this is very easy to find the difference between dogs and cats, but computers should take the image and dig into the details of each image. Computers look over the image pixel by pixel to find a pattern or feature to label it as a cat or dog. As the name of deep learning emphasizes, these models go into a deeper representation of data in each step. Generally, deep learning models consist of different layers. These layers are arranged spatially. As we step further in layers, we extract deeper and more complicated patterns in the data. As we can see in this image, we focus on the general and simpler patterns in the first layer. We detect some curves in different parts of the cat. Each particular image has some special features that help the computers to learn some patterns from them. Computers will learn patterns gradually and improve their patterns by taking more data. As we go deeper in the layer, the detected patterns become more complicated. As we can see, the complicated patterns are generated by combining the simpler patterns from the previous layer. These patterns, which have been learned by the DL model, are called filters. How does the convolution operator work? As we can see in this graphical representation, the yellow square is the kernel and green square is the input data. The pink matrix is the output of the convolution. To calculate the output of a convolutional layer, we move the kernel matrix over the input image and calculate the dot production of the kernel with the covered elements of the input matrix. As we can see, we have a reduction in the size of matrix in 2 dimensions. In this slide, I want to demonstrate the difference between 3 basic definitions. We use kernel and filter terms interchangeably, but their definitions are different. In each convolutional layer, we perform lots of kernels over the input image. The series of kernels that are performed on the image is called a filter. The output of the filtered image is itself an image. A layer is a series of filters. Filters are multiple kernels that perform on a multi-channel image. Let's go back to this slide. We call each of these patterns a filter. These patterns construct the layer. If the input data has just one channel, the filter just contains one kernel. In different depths of the network, we face multi-channel data. Multi-channel data needs multiple kernels. A normal convolution consists of multiple kernels for a multi-channel image, and after performing each kernel on each channel separately, it adds them together to reach a single channel output. To reach multi-channel output, we use multiple filters. According to this animation, each kernel operates on each channel, and then the value of the output is the summation of these 3 values. We can repeat it with multiple filters. As we saw in previous slides, the dimensions of the input image decrease during the convolution operation across x and y axes. For example, in this figure, the dimensions of the input image is 5 by 5, but the output dimension decreases to 3 by 3. To prevent this issue, we can add some pixels around the input image. The value of these pixels can be equal to the value of the pixels on the edge of the input image. This operation builds a 7 by 7 input image, and the output will be 5 by 5. So the dimensional reduction has been prevented. Note that in this example, the kernel was 3 by 3. For kernels with other dimensions, the number of padded pixels should be changed. In the previous slides, the kernel has slid over the image pixel by pixel. If we consider a center for the kernel, the center of the kernel in each step has just been moved to 1 pixel. We can change the stride size of the kernel movements. In this image, the center of the kernel has been moved 2 pixels in each step. This operation decreases the size of the data faster. We can see that the dimensions of the input image have been halved. So the output of the 2 by 2 stride convolution is 2 by 2 according to the input 5 by 5. That concludes everything I intended to express in this video. Thank you for watching this video. We look forward to seeing you in our upcoming videos.